squared plus 3x divided by 2x squared plus 10x plus 12. We're going to discuss domain, intercepts, asymptotes, critical numbers, intervals of increase-decrease, inflection points, and concavity. Depending on what specific application we're trying to do, this could relate to finding max and mins. This could relate to talking about elasticity. This could relate to simply optimizing an equation. All of these skills are involved in the idea of sketching the graph. This is sort of the big feature that uses everything. To discuss domain, I'm going to take this and I'm going to first factor the top and the bottom. On the top, I notice that both terms share an x, so I factor that out and I'm left with x times x plus 3. On the bottom, I have some options. To discuss domain, I need to care about where is f of x undefined. And f of x is going to be undefined. Its denominator is 0. And those happen in two places, where 2x plus 4 equals 0, or where x plus 3 equals 0. Solving these two equations tells me that either x equals negative 2 or x equals negative 3. These are two numbers that are not part of my domain, so at the end of the day my domain is everything except those two numbers. So I go from negative infinity to negative 3, then I go from negative 3 to negative 2. I'm willing to include points in between minus 3 and minus 2, and finally I go from minus 2 all the way up to positive infinity. So this right here is going to be my domain. Alright, to talk about intercepts, I've got two types of intercepts. There's y-intercepts. Y-intercepts occur when my function has 0 replaced into the x's. It happens when x equals 0. That's when I'm going to cross the y-axis. Plugging 0 into that original equation gives me 0 squared plus 3 times 0, all divided by 2 times 0 squared plus 10 times 0 squared plus 12. At the end of the day, this equals 0 over 12, which just equals 0. So I have a y-intercept at the point 0, 0. Notice this is also an x-intercept because this is the one point that's on both the x and the y-axes. This is my only intercept. To talk about asymptotes, asymptotes come in two flavors. There's vertical asymptotes. Vertical asymptotes happen at places where the denominator, or the function's denominator, is undefined, which means it involves this domain idea. I've got these two numbers here, but we have to observe something. Looking back over here at the original function, once I've factored it, some cancellation happens. That means x equals minus 3. It's a problem. I still can't plug him into this denominator, but he's not as big of a problem. So for vertical asymptotes, I'm going to get a vertical asymptote at the place x equals minus 2. However, for x equals minus 3, I'm simply going to get a limit point And that limit point is going to have a very particular place. It's going to be at negative 3, f of minus 3. If I plug negative 3 into my simplified equation up here, which is just x over 2x plus 4, take this negative 3, I plug them into these two spots for x, and I'm going to get negative 3 over negative 6 plus 4, which is going to be negative 3 over negative 2, which is just 3 halves. So I'm going to get myself a limit point. At the point negative 3, 3 halves. So I have a limit point, I have a vertical asymptote, and now I want to talk about a horizontal asymptote. Horizontal asymptotes happen when the limit of x goes off to infinity. I'm going to plug this back into the original equation, x squared plus 3x over 2x squared plus 10x plus 12. And as I'm doing this, I'm going to be remembering some fact. And when I have a fraction, when overall I have a fraction, and I'm taking an infinite limit, I have this trick. And this trick is that I multiply the top and the bottom of the fraction by 1 over whatever the highest power of x may be, which here it's x squared. Once I've done this and distribute it, I get something convenient. My limit, as x goes off to infinity, once I've distributed this 1 over x squared term to the top and the bottom, is going to give me something useful. It's going to give me x squared over x squared plus 3x over x squared. This is something perfectly legitimate to do because 1 over x squared divided by 1 over x squared is simply 1. This term right here, I'm just multiplying by 1. So, on the bottom I get 2x squared over x squared plus 10x over x squared plus 12 over x squared. At this point some cancellation happens, and I'm left with the limit as x goes off to infinity of 1 plus 3 over x, all divided by 2, plus 10 over x, plus 12 over x squared. We have something special that's happening on these terms. These are numbers, constant numbers, 3, 10, and 12, and they're getting divided by x, which is getting very large. So 3 over 10, 3 over 100, 3 over 1,000. As x gets big, this whole thing goes off to infinity. It's because I'm dividing by x, and x is getting very large, that this goes off to 0. So at the end of the day, I just have 1 over 2. This means I have a horizontal asymptote at y equals 1/2. So I've talked about domains, intercepts, and asymptotes. It's now time to talk about critical numbers. I'm going to take my simplified form of the function f of x equals x over 2x plus 4, and I'm going to find the derivative, because critical numbers come out of the first derivative. To find the first derivative, I'm going to have to use the quotient rule. And as I'm using the quotient rule, I'm just going to take this a piece at a time. The quotient rule says I take the bottom, and I don't change it, and I multiply by the derivative of the top part. The derivative of x is just 1. Then I subtract the top part unchanged, which is x, and I multiply that by the derivative of the bottom, which is just 2. This is all going to be divided by the bottom part, 2x plus 4 squared. This can be algebraically simplified to be 2x plus 4 minus 2x on top, all divided by 2x plus 4 squared. I'm not going to FOIL the denominator. I usually factor denominators. I spend a lot of time doing that. I notice that 2x and minus 2x cancel, and so this gives me my final algebraic form of my first derivative, which is going to be 4 divided by 2x plus 4 squared. I can convert this, though, into a slightly different format, 2x plus 4 to the negative 2, by pulling that 2 up from the denominator. And this will be the form that I'm going to use for my second derivative. So I'm going to use this to find f double prime of x. However, this part right here is what I'm going to use to find critical numbers. So, taking my critical number form of this, critical numbers come from 3 spots really. The place where the first derivative is equal to 0, places where the first derivative is not defined, and also places where I have endpoints. Endpoints of my original equation from my original domain. Endpoints from the domain. Going back up and looking at my domain, I don't have endpoints because I have negative infinity on one side and I have positive infinity on the other side. So I'm not going to get any endpoints. At my first derivative, I have 4 over 2x plus 4 squared and this guy's never going to equal 0. If we try setting him equal 0, then I'd multiply both sides by 2x plus 4 squared, and that would on the left cancel, but on the right I would be getting 0 times 2x plus 4 squared, which would tell me 4 equals 0. I don't get any inputs from my domain. I'm not getting any place where my first derivative is equal to 0. If I'm going to get any critical numbers, it's going to have to be where the first derivative is undefined. The first derivative is undefined when I'm dividing by 0. So undefined happens when 2x plus 4 equals 0, which means 2x equals negative 4, which means x equals negative 2. This is my only critical number, and what I do with critical numbers is this. I make a number line, I write my critical number down, I then take a test point on either side of each critical number. Here I only have one. I think I like the points 4 and 0. I take these test points and I plug them back into the first derivative. I don't care about what exactly I get out of the first derivative, I just care about whether it's positive or negative. So I take minus 4, I plug it into the first derivative, and that's going to give me 4 over 2 times negative 4 plus 4 squared. And at the end of the day, because I'm squaring everything in the denominator, this will leave me with a positive, which means my original function is increasing from negative infinity to minus 2. If I plug 0 into the first derivative, I'm going to get 4 divided by 2 times 0 plus 4, all of this squared. Once again, this is positive, so my first derivative tells me that my original function is always going to be increasing. I'm going to take this simplified form of my first derivative. When I use power and chain rule, I'm going to pull that minus 2 down in front. There's still the 4. I'm going to keep the inside 2x plus 4 exactly as it is, to the minus 3 now, and then I'm going to multiply by the derivative of the inside, which is once again just 2. This becomes negative 16 over 2x plus 4 to the negative 3. Which is negative 16 over 2x plus 4 cubed. This is my second derivative. I'm going to use this to find inflection points. And inflection points occur when either my first derivative is giving me a second derivative equal to 0, or when my second derivative is undefined. Again, because there's a negative 16 here on top, I'm not going to have a place where my second derivative is equal to 0. That's just not going to happen. And once again, because the bottom part is 2x plus 4 equals 0, x equals negative 2 once again becomes my only inflection point. For my inflection point, I take that negative 2, my test points, but I'm dealing with second derivative now, so I'm going to plug those into my second derivative. When I plug those into my second derivative, I'm going to be taking negative 16 over 2 times negative 4 plus 4. This time it's going to be cubed. This will give me a negative over a negative, which is a positive, and positive means concave up. When I plug in 0 into my second derivative, I'm going to get negative 16 over 4 cubed. This is a negative over a positive, which is a negative, and that means I'm concave down. This concavity and this increase-decrease, I've recopied them down here already. And now I'm going to use them to draw my graph. When I'm drawing my graph, I first talk about my asymptotes. Remember, I had a vertical asymptote here at negative 2, and at the point negative 3 3/2, I had a limit circle. Here's the point negative 3. I go up 1/2, 2/2, 3/2. I draw myself an empty circle. On my actual graph, remember I had the origin point 0, 0, and also remember I had a horizontal asymptote through the point y equals 1/2. When I'm drawing my graphs, I need to be from negative infinity to infinity. I need to be increasing, and I need to be concave up, which means I look like this. When I'm going from negative 2 to positive infinity, I need to be increasing, I need to be concave down, and I need to go through the origin point, which means I look like this.